Alright, so starting with number 1, we have exponential and log equations. So we just want to use our different methods that we use for solving the particular exponential or log equation. For the first one, A, we see it's an exponential equation. We have an exponential set equal to number, so we can either try to do one-to-one property, which means the bases need to be the same. If we can't get that, then we natural log both sides. We can't get like bases. 3 can't be 2 to some whole number exponent, so we are going to, kind of hard to write it in here, but we're natural logging both sides. We natural log both sides, the exponent x plus 4 comes in front, and then we have natural log 2, and this side we have natural log 3. Now we want to look at this as far as a linear equation, where natural log 2 and natural log 3, as far as solving for x, we think of it as a constant, just like a 4 or a 2 added or subtracted or multiplied divided by x. But when we're combining like terms, you want to think of it as variables. So there's two ways we can go about this. We could divide by natural log 2 on both sides and then subtract the 4 over. The other way is distributing it and moving it to the other side. In class, I showed the distributing and then the distributing method and then the solving for x. This time I'm going to divide by, first just by the natural log of 2, so I have natural log 3 divided by natural log 2, and then if we subtract 4 over, we get our final answer, exact answer of natural log 3, natural log 2, minus 4, and since we're giving exact answers, we are done right there. If it was calculator, you just simply plug in your calculator, make sure you do it correctly, and round accordingly. So in this one, we don't even have to solve because this is a no solution because our logarithm has a negative argument. That means, why is that not possible? Well, that logarithm means 5 to what exponent gives us negative 7. Can't take 5 to some exponent to get a negative number, so here we have no solution. Moving on to number 3, we have a couple things happening here. One, we have an exponential equation, so we want to get this set equal to a number, which we do, but we could simplify this first before we go about trying to solve for x. So if we simplify this, we multiply these exponents, and we can combine these by doing root 3 times root 3 is 3, and now we have 3 times 4 is square root of 3 to the 12th. And as we discussed in class, this is an index of 2, and a different way of writing that would be in exponent form, which is 12 divided by the index, which from the radical, or another way of saying the radical is an exponent, it's the denominator of the true exponent of the term. And so we have 12 over 2, which is 3 to the 6th. And if you plug 3 to the 6th in the calculator, you get 729. So 3 to the 6th is 729, and I have e to the x minus 3. Two ways you could look at this, either putting it into logarithm form, or you could think of it as natural logging both sides. If we put into logarithm form, it's a log with a base of e, which we raise natural log. We put the value right here, which is now the argument of the logarithm, and then our exponent is x minus 3, and then we will add 3 to both sides. I am preferably going to write, I think it's preferable to write the constant in front, so then it doesn't look like your solution. Natural log 729 plus 3, the 729 plus 3 is all in the argument. If we natural log both sides, we get literally the exact same thing. Alright, find the domain and range of each function. Even if this is done without a calculator, this is fairly easy to do if we know how to sketch a graph. So if we have our exponential function e to the x, we're going to transform that. First, we have the reflection about the x-axis, so I have e to the x would look like this, and negative on the outside means our outputs are going to go from this to this. And with that reflection, the asymptote is right here, and then we have the plus 2, so that moves our asymptote up 2. And also, if you recall from your notes from 3.1, our model of b a to the x minus c plus d, b is the coefficient of e, which is negative 1, and the d, the vertical shift is 2. That also tells us where our horizontal asymptote is. So with that being said, -1 is our b value, which tells us the distance from the asymptote to our key point. Well, -1 means down 1, so therefore we have our point right here. That also would have made sense if our original e to the x, if we thought of it this way, if our original e to the x is 1, 0, 1 is our key point. We reflected about the x-axis because of the reflection. And note, this is on the outside, that's on the outside of the function, so it has to go in that order. So if I reflected this down to 0, -1, and then I had the +2, that would move it up here. So either case that we look at it, we get the key point at 0, 1, and that is going down as, again, the original function of e to the x has been reflected that way. Now we can find our domain. Domain's pretty straightforward. So we go from -infinity to infinity. We don't have any breaks in the graph. So domain is -infinity to infinity. Range going down to up, so you start at -infinity, and then you have an output up until the value of 2, but not including it, so m parenthesis. Next we have -3 plus log base 7 of x. Log base 7 of x we can essentially treat like, let's go and draw our xy axis here. We can essentially treat like log base 2 of x or natural log of x. It has a base greater than 1, so this is logarithmic growth. It's going to look like this, generally speaking, and our key point is 0 or 1, 0. There is no transformation other than -3, so if we take that point and move it down 3, we are now at the point 1, -3. We have a vertical asymptote at x equals 0. Well, if we're shifting that down 3, that's not changing that asymptote at all. And now there's nothing else going on there, so we just sketching it, where I cross that x-axis may have not been accurate, but that doesn't matter. Our goal is simply just to get an accurate domain and range. So our domain is 0 to infinity, and then our range is -infinity to infinity, because we're simply going down to up, and there's no breaks in the graph. Coming to here, that would be logarithm base graph. Our parent function graph looks like this. We have reflection on the inside and the outside. So if we're going like this, when we first reflection on the, again, it doesn't matter what order if we do the reflections. I'm just going to go over the y-axis first, and that would be from the negative on the inside. So if I do that, it's going to reflect, and it's going to look like this. And then this is now going to reflect over the y-axis. So instead of coming up to down, if we move like that, down to up, going like that, we're now going to go like that. Let's go like this. It's going to intersect. Let's see. Where's that intersection point going to be? So if I have it at 1, 0, I've reflected about the x-axis, and now I'm flipping it about the y-axis, which doesn't change that point at all. So our key point has been reflected to the point -1, 0, and we have a vertical asymptote. I'll just do it within shaded red right there. Okay, so our domain would be, as we see, going from left to right, we have -infinity to 0, range, all real numbers. Sorry for the sloppy infinities. I heard sometimes they're right on the iPad. Alright, so we got quite an interesting one here. So if we just had log base 2 of x, we would just have our basic log function, and we go domain from 0 to infinity, range to infinity to infinity. However, now we have something more happening on the inside here. Well, we do know that this argument has to be greater than 0, because again, this is the value of the power term, which we call the argument in the logarithm. If we go 2 to the y, the 2 to any number is always going to give you a positive number, so this can't be greater than, or that has to be greater than 0. So if I solve, I get x squared greater than 9. When I square root, I get x greater than 3, and then I have an or x less than -3. When you think of that like x equals plus or minus 3, when you have those two solutions in inequality, that second one, the negative, you think of it very similar to dividing by a negative flips the inequality sign. And of course, we could also test this out. this is a graph, x squared minus 9, that's a parabola that would be shifted up 9. And if we wanted to know where it's, I'm sorry, shifted down 9, right? So if we want to know where this parabola, which is shifted down 9, is greater than 0, the outputs of it, that would be on these values. So that's going to be our domain right there. So our domain is going to go from -infinity up to -3, which takes care of this part. Union with 3 to infinity. And then our range. This range is a little trickier, but what I would do is look at, okay, well, what's the least value that we can plug in terms of, oh, sorry, clean that up, this would be -3. So really, if I plug in -3 or +3, I'm going to get the same output because the that input is being squared. So let's just look at some values. And of course, if we had a graph, we could just look at the graph and go, okay, here's a range. But we could also do this just by checking our input. So if I start at 3, because that's my least value, and again, these don't matter because squaring it, these will get the same outputs as these. So let's just start with 3. If I plug 3 in, I get 3 squared is 9, 9 minus 9 is 0. So 2 to what power gives us 0? That would be 1. So our value, our output, when our input is 3, our output is 1. So that's probably going to be on either side of our range, either the beginning of our range or the end of our range. Now if I plug in another number, let's say if I plug in 4, I get 16 minus 9 is 7, log base 2 of 7. It's not this nice neat number, but log base 2 of 4 is 2, and log base 2 of 8 is 3. So log base 2 is 7, somewhere between 2 and 3. And remember, we started with the input of 3, gave us a 1, and now that we increased our value, our y value's increasing, our output's increasing as well. We could just do one more check on it. Let's say if I plug in 5, if I plug in 5, I get 5 squared is 25. 25 minus 9 is 16. So log base 2 is 16. Actually, that gives us a nice neat number of 4. So we see our outputs are, as x is increasing from 3 to infinity, our outputs are increasing as well. And there's no limit on that after that. I mean, we could plug in 100 for x, we could plug in 1,000, 10,000, and so on. That number's just going to get bigger and bigger. So the least value for our range is 1, and it is an output because log base 2 of 0 is 1, and then that goes off to infinity. So next I want you to graph this along with specify the domain, range, and all of that, intercepts and asymptote. So we don't need to use an input-output. We could just use our base parent function of a logarithmic growth with a key point at 1, 0, an asymptote of x equals 0, and then we just transform from there. So if you look at the transformations, we have a right 1 because it's on the inside, and then a +3. So I'm going to take my point of 1, 0 and move right 1 and up 3. So I'm going to start here. I'm going to move right 1 and then up 3. Puts us at the coordinate 2, 4. And then our asymptote is at, as we know, with the parent function is at x equals 0. So we're going to come over here and ask ourselves, if we move a vertical asymptote to the right 1 and up 3, use a vertical asymptote up or down, it's really not changing. So what we need to do with this asymptote is just the right 1, which puts us at an x value of 1. And then we know it's logarithmic growth, there's no reflections. We're just sketching at that point. Remember, the three key characteristics to get full credit on a graph when you're sketching is your key point, wherever that gets transformed to. And I just did realize that it should have been +3. I got mixed up here as I was doing that, my apologies. So up 1 and then 3, so I should be at the coordinate 2, 3, not 2, 4. So I'm just going to change it up really quick, 2, 3. And then erase that other one. Okay, so now that we have that, we can go ahead and do our calculations as far as domain and range. If you look at the domain, I'm just going to write it here in the interest of not having to keep moving this over to the left. Domain is from left to right, so 1 to infinity, not including 1, since that is your Asymptote range is infinity, negative infinity, infinity, no restrictions on the range. Intercepts, we want to find the x-intercept. We're going to plug 0 in for y. I'll come over here. So when we plug 0 in for f of x, since we're looking for the x-intercept, we plug 0 in for y. I want to get the logarithm by itself, so I subtract the 3 over, and I get log base 3 of x minus 1. And now we have 3 to the negative third equals our argument, which is x minus 1. And that would solve if we get x equals 1 over 27. As I took this, I flipped it to the denominator, turned the exponent positive. 3 to the third is 27. And then we have a plus 1. So if we want to combine those, that would be 27 over 27 plus 1 over 27, which gives us 28 over 27, or the x-intercept at 28 over 7, comma 0. For the y-intercept, it's going to come right over here. I'm going to plug, I'll just draw a line here, f of 0 equals 3 plus log base 3 of 0 minus 1. And when we plug 0 in, we end up getting a negative argument, which means we do not have a y-intercept, so there's none. And that makes sense with this graph. As you see, we're never going to hit the y-intercept. And then lastly, our vertical asymptote. Oh, I said hit the y-intercept. I meant hit the y-axis, but I think you know what I meant. Vertical asymptote is going to be x equals 1. All right, for finding the inverse is a straightforward process that we've done in the past with other functions or equations. Basic first step is interchanging the x and y. So y becomes x and x becomes y. Our goal is to solve for y. So for an exponential form and y is in the exponent, we need to solve. We're going to natural log both sides. So I'll put this in here as best as possible. I think I can fit it in. There we go. So now we rewrite. So I have natural log x equals the y comes in front, the negative y comes in front, natural log 3. And now our goal is to solve for y. So we need to divide by, we need that get rid of the negative, so we divide by a negative natural log 3. You can think of the negative out front as a negative 1. So we need to divide by negative 1 and the natural log. I'm going to rewrite y with the y on the left-hand side. Rewrite gives us y equals the opposite of natural log x divided by natural log 3. Another way we could do it is simply go from, when we get back to this step where we have x equal to 3 to the negative y, we could simply put that into logarithm form. If we did that, we have log base 3, because 3 is the base of the exponent, of the value, which then becomes the argument, equals negative y. And now we divide by negative 1, so we get y equals the opposite of log base 3 of x. Both of those are the same, just in different forms. If you look at this, if we did change a base roll on this, we get natural log x over natural log 3 with the negative out front, which is the same as this. So just be aware of different forms of the same result, particularly for like a multiple choice answer. But ultimately, I think this would be your best bet in terms of what would be a most acceptable form of the inverse. Okay, same here. Let's go ahead and solve. Y equals x to the 7th, and we could just leave it right there. Last one, again, if we interchange the x and y, and then go ahead and simply put into logarithm form, or natural log both sides would give us the same thing because we have a base of e, so we have natural log, that's log base e of the value, which is now the argument, which is x, equals the exponent, which is y minus 3. We're now going to solve for y and switch sides, so I'm going to switch y to the left-hand side. I'm going to add 3, so I have 3 plus natural log x, and I just decided to put the natural, or the 3 out in front so it doesn't look like it's part of the argument. Okay, so determining which two integers log base 4 of 87 is between, you should be able to do this without a calculator, and the base given 4 will be a reasonable base on the test, like 2, 3, 4, where you can easily know your powers of them. So to check this, just to help understand why we're getting the result we do, let's look at our powers of 4. So if we list all of those, we have 4 to the third equals 64, 4 to the fourth equals 256, and note for me to do a calculation like 4 to the fourth without a calculator, anything in the fourth, I think of what 4 squared is, 16, and then multiply that by itself, and you can get 256 fairly easy that way. So what we're doing now is we're looking at 87. Remember, 87 is our value of the power, so we want to see where 87 is relative to all of the 4 to the power of a whole number for the 0, first, second, and so on. And 87 is between 64 and 256. So if this value is between, or this argument's between the 64 and 256, then the whole value of the logarithm, which is the exponent, is somewhere between 3 and 4. Okay, so 3 and 4 would be your answer. Coming over to 9, if we start out at 9 to the 0 equals 1, 9 to the first equals 9, and so on. We can stop right there because 2 is between 1 and 9. Therefore, the logarithm is going to be between 0 and 1. Lastly, we have natural logs. E to the first is about 2.7. E to the second is in the range of about 7.3. If you go e to the third, that'd be about 7.3 times 2.7. Gives us somewhere in the 18 to 20 range, and of course you could use your calculator for this, but if we're looking at a non-calculator, obviously we need to make some estimates here. So e to the fourth, if that's about 20 times 7, it's probably in the neighborhood of 140-ish. And again, of course, we could check that on the calculator. But if we're looking at 30, 30 is between the 20 and the 40, so that's between a 3 and a 4. So if this is between a 3 and a 4 and we're adding it to 2, that would ultimately put this whole expression between a 5 and a 6. Just quick once again. Natural log 30 is somewhere between 3 and 4. And we're adding that to 2, so if I add 2 to 3 and add to 4, if I add 2 to 3 and 2 to 4, that puts us in the neighborhood of 5, between the integers of 5 and 6. Coming down to number 6, where we are now working on condensing logarithms. First one here, we're looking at, we have a quadratic in this first logarithm, and then we have subtraction of the addition of these two. So first off, we could condense this, and I think it would be factor the quadratic. So when I factor that, I see I have negative 56, multiplies me negative 56, and adds to be 1. So that is going to give us x plus 8, x minus 7. Also, I have that subtraction, and I'm going to combine or condense those to log base 2 of 8x. And now, as I look at this, I have two logarithms with the same base. Subtracting, I can condense those down into one logarithm with the base of 2. And the positive logarithm, which was the first one, that argument goes in the numerator. And the negative logarithm, minus log base 2 of 8x, that argument goes into the denominator. Just to be clear, up here for subtracting both of these, if I distributed both of those would be both negative logarithms, and therefore both of those arguments be multiplied in the denominator, which just reconfirms the setup that we have here. Why did I factor this? Well, it could be possible that this argument and this argument were, we had like an x plus 8 or x minus 7 down here, and they cancel, so that's why I thought it was important to factor that. Coming over to B, a little more complicated, but we still have the same setup or same ideas happening in terms of condensing. If we have a positive logarithm and two negatives, the positive logarithm argument is going to go in the numerator. The two negative logarithms, those arguments are going to go in the denominator. I'm going to do this in two steps. I'm going to condense this, and then I'm going to distribute in the two. Of course, you could distribute in the two originally and then do your condensing. But I'm deciding to leave that 2 out front. I'm going to take this 3 and bring that to the exponent of the argument. So first off, I know that I'm going to condense into a natural log. I have positive and negative logarithms, so I want to have my division bar to separate my numerator and denominator arguments. This one, since this is our positive logarithm, that's going to go in the numerator. And again, that 3 went into the exponent of x, so I have x to the third in the numerator. And then these two are negative logarithms, so those arguments are going to go in the denominator being multiplied by each other, which was also, I gave a little more instruction on in the last problem, problem A, where the two logarithms being added together with a negative on the outside condensed and gave us the same result, where those both are in the denominator. Now this 2 is out in front of the whole logarithm, so this needs to go to the whole, or needs to go to the exponent of the whole argument, which means then we would distribute that in to each part. So rewriting this, I have natural log of x. If I bring the 2 up there, it's 3 times through the 2, so that gives us x to the 6th, x plus 1 squared, x minus 1 squared. Coming down to 7, now we're expanding. So when we expand, we're simply using the condensing expanding rules in the reverse order of what we just did. So if I have a term in the numerator of the argument, that's going to be a positive logarithm, this is going to be a negative, and then after I split these up, then we'll go ahead and deal with this radical. So first one, I have natural log 6, that's a positive logarithm, and then minus natural log root x squared plus 1, and that's a negative logarithm since that argument was originally in the denominator of the logarithm. Now we need to take care of this root in expanded form. Keep in mind that roots are fractional exponents, so there's a fractional exponent of a half. So I'm going to make my life a little easier. I'm going to cross that off and rewrite it as an exponent of a half. That's going to come in front of the logarithm. So now we have natural log 6 minus 1/2 natural log, and now I'm just going to put this in parentheses, x squared plus 1. There's nothing I can do with that x squared plus 1. Just a note that addition in the condensed form, there are no properties for that. So we leave that as is, and we think of that all as one term. Not that there's anything to do with that, I just wanted to give a little description on what's a correct way of thinking about, or at least in my estimation, a correct way of thinking about that argument. Okay, coming to B, pretty much the same thing. I think for this one, I'm going to take care of this radical before expanding it out. Since these are being multiplied, we can quote-unquote distribute this radical to both of these. So if I do the square root of x squared, that's going to give me an x. So of log base 4, I'm just going to go ahead and rewrite this. X and then root x plus 2. I lost a parentheses there. You could write the parentheses if you want. And now, again, because of this addition in the condensed form, you want to think of that all as one term. So ultimately, we have two terms, the x and the root x plus 2 in this argument. We're going to split it by expanding. So I have log base 4 of x plus, and I also have the second one, log base 4 of x plus 2. And instead of, because I know that we are going to move this radical, which is fractional exponent in front, I go ahead and write it as a half right away. And then I'm going to bring that half in front. Instead of rewriting the whole thing, I'm just going to erase that. And that would be your final answer. Okay, coming to evaluating some expressions. This should be able to be done without a calculator, and this uses our knowledge of what a logarithm is and making sure we know how to think in logarithmic terms to do calculations. Meaning 4, the way I say it in words, is 4 to what exponent or 4 to what power would give us 2? Well, you need to square root 4 in order to get 2 in terms of exponents. Of course, we could divide 4 by 2 and get 2, but that's not what we're talking about. We're talking about exponents. So 4 to what power would give us 2? We would square root it. Square root as an exponent is in half. For the next one, probably got to do a little work here. Multiple ways we could go about this. I think given that we have 4 to what power gives us 2, there's multiple 2's here being multiplied together. Since we have 2 to the first and 2 to the fourth, we put that together, that'd be 2 to the fifth. 2 to the fifth would give us 32. And then I think, okay, 4 to what power gives us 32? That's not a whole number, so I don't really want to go that route. I'm going to try splitting this up into by doing expanding rules and see where that takes me. So if I split that up, I have log base 4 of 2 plus log base 4 of 2 to the fourth. Now I'm starting like this because I know what log base 4 of 2 equals, which is right here. It's going to be a half again. And I also know on this next one, I can pull this exponent in front, which would be 4, and then I have another, after I pull this exponent in front, the logger on the left is log base 4 of 2, which ends up giving us a half. So now I see a half plus a half plus a half plus 4 gives us 4 plus a half. So we would have, 4 plus 3 halves, and then that'd be 8 over 2 or 11 over 2 or 5.5 if we hit in decimal form. Coming over to B here, this is the exponent with a logarithm rule that we want to try to use, which I'll go ahead and write that property again. It was a to the log base a of x. We found that to be x by, if we put this into logarithm form, with this being a log base a of x equals blank, you put that into logarithm form, you would find you would need to put x into that blank in order to make the equation true. So the point being of this property is if we have a power term, the base is a, logarithm is the exponent, as long as that base right there, a, is the same base as this one, the whole expression is equal to the argument of the logarithm. Problem is right here is we have a base of 4 here. We also can't calculate log base 4 of 9. So I'm going to focus in on this and say, okay, well, what could I do to this in order to make this the same as that base? And the way I can do that is changing 2 into the square root of 4, or in exponent form, that'd be 4 to the half. So I'm literally replacing 2 with 4 to the half, and now that is being taken to the log base 4 of 9. Now we're not there all the way. We want to get to this form where bases are the same and it's just a logarithm. So right now we have this times that, 1/2 times that, and to get this, we need to get this half out in front of the logarithm. Well, the way we do that is we bring it to the exponent. So if I bring that to the exponent of the logarithm, logarithmic argument. So if now I have log base 4 and I bring this half to the exponent of 9, that's 9 to the half power. Half as a power or an exponent is a radical, so that's the square root of 9. And now in our argument, the square root of 9 just gives us 3. And now we have this form here where here's our a, here's our a, here's the value of the argument. So ultimately, this whole expression equals 3. Same sort of idea, I guess, that we're working with here. This is kind of, as I've expressed in class, just kind of like numeric or algebraic gymnastics of logarithms, which is really important to sharpen our skills as far as dealing with these logarithmic expressions and exponents. Given the fact that the way I look at this, I go, okay, if I see as natural log, and I also see this e here, I know that natural log and e, if it was just by itself, would cancel, would be 1. So if I can somehow exploit that by taking care of these exponents somehow, I can probably have a really nice way of simplifying this. So what keys in here is I can put this exponent as e to the 3/4, and I go, okay, now if I get this all into one exponent, or e with just an exponent in the argument, I can then move it out front. So that's what I'm going to do. I'm going to change this to e, and then that exponent would be 3/4. Once again, the true exponent of a power is the exponent e to the third, what we typically think of as our exponent. That's the numerator of the true exponent divided by the index of the radical. And as I've been covering in other problems in this video as well, when we take this and move it out front, we now have 3, and by the way, using the power property when we move that out front. And now we have 3/4 natural log e, and natural log e equals 1, so we're left with 3/4. All right, so number 9 here brings us back to, again, as I kind of expressed before, like logarithmic or algebraic gymnastics. We're practicing some skills to sharpen our skills on logarithmic expressions and the relationships of them. We have these log base b of 2 equals a, log base b of 3 equals b, and log base b of 5 equals c. And what we want to do is get this, whatever expression we're given, get it in terms of a, b, and or c. So as we look at log base b of 60, we want to get 60 in terms of 2, 3, and or 5 in some capacity. So we can factor 60. One way we could do factor 60 would be 30 times 2. That works nicely because we got a 2 there. We could also go 15 times 4. And if I go 15 times 4, I know 4 has 2 as a factor, and then 15 has 3 and 5. So I think that might be a good route to go. So I'm going to try that. So I'm going to go 15 times 4, and then I'm going to try breaking that down some more. So I now have 15. I'm going to break that down into 5 times 3. And then I'm going to make the 4 2 squared. Again, I'm trying to get this number 16 in terms of 2, 3, and or 5. And so when I take that route, now I can break up each of those logarithms by expanding it. It's very important to expand it all the way before you insert your a, b's, and or c's. So now I have log base b of 5, log base b of 3, and then plus 2 log base b of 2. I did 2 steps there. One, I broke the logarithms up, and on this one, I also pulled the exponent down in front. And now we can do our substitution. Log base b of 5 is equal to c. This is b, and this would be 2 times a, and of course the order, you can rearrange it. All right, so when we come to b, at first this may look fairly straightforward because we have a 5 and a 2, but the problem is our base of the logarithm is 3, not b, because all of our substitutions have log base b. So that indicates to us that we're going to have to use change of base rule and see how things go. So first off, I want to change this up into log base b over log base b. Note when we do change of base, you can choose any base you want here. Typically, we choose, if we're doing calculations, we choose e or 10 because that's what our calculator can use. But now if we use log base b of b, we can get our numbers here, 5, 2, and 3, in whatever capacity in terms of the expressions that were originally given. So our change of base formula states that, again, you can choose any base, and then our argument in the numerator here is going to be the argument of the original logarithm. So we have a 5 over 2 here, and then the argument of our denominator logarithm is going to be the base of the initial logarithm. Now we have in the denominator log base b of 3, which is equal to b, and in the numerator we'd expand that into, I'm just not going to write, I'm just going to say it, log base b of 5 minus log base b of 2, which would be c minus a. Same here, since we have log of 5, base of 5, we want to switch this up to our log base b using change of base. Argument will go b in the numerator here, and then base of the logarithm 5 is going to go in the denominator here. Log base b of b is actually we can calculate that. B to what power gives us b would equal 1. And then the denominator log base b of 5 is equal to c, so 1 over c is our final answer. All right, coming down to number 10, this problem, I will demonstrate here what is probably the most common understandable mistake that I've seen over the years in terms of how students approach this. They see whether this exponential term e to the 2x is by itself or not. Students get here and they go, oh, okay, it's an exponential equation, and I'm going to want to pull down this x, so I'm going to like natural log both sides. If you look at that algebraically, it's kind of sloppy there. There's not much room. But right here, if I go natural log of this, I could pull the 2x in front. I cancel out the e. But over here, we have parentheses here around all of this because we'd be natural logging both those terms, and you can't do anything with that. So that's not a way. We can't natural log both sides to solve for x because we have these multiple terms right here. So the way that we're going to handle this is hopefully recognize that this is a quadratic where our variable is e to the x. So here we have e to the x squared, even though it's written as 2x, is really e to the x because we can flip these two around. It'd be e to the x squared. This is e to the x, and then we have our constant plus 6. So since it's a quadratic, we want to get every term to the same side. So I'm going to subtract over those two terms to keep my a term positive. And we can also do what's called a let statement to just, as I like to say, it makes it easier on the eyes. I'm going to choose a typical preferred variable is u. It's typically called u substitution. But I like using a, so I'm going to use a. And this really is doing nothing other, like I said, than making this easier on the eyes. So imagine right here, I'm going to flip the x and the 2 around, and I'm going to quote-unquote factor out the 2, or just think of that as e to the x, that variable, or that term squared. And now, since e to the x equals a, I can substitute that in, and now this e to the 2x is equal to a squared minus 5a minus 6 equals 0. And our end goal is not to solve for a, our end goal is to solve for x. So after we solve for a, we're going to substitute e to the x back in, and then solve accordingly. So now that we have this quadratic, what multiplies to be -6 and adds to be -5, that would be -6 and +1. So we factor that, set those equal to 0, and now we have a equal to 6, a equal to -1. And again, we're not solving for a, we're solving for x. So we're going to substitute e to the x back in. E to the x equals -1. And now if I take e to the x, first one equals 6, I put that into log form. Natural log with 6, because that's our value, so that goes in the argument spot, equals the exponent x, and now we have x equal to natural log 6. Over here, e to the x cannot equal 1, so that's a no solution. We cross it off. For b, we have an exponential equation. We look at that whenever we have an exponential equation. We want to first look for one-to-one property, see if we can get bases equal, and we can. 9 and 27 can both be written with a base of b. So instead of writing as 9, I'm going to write as 3 squared, and that 3 squares be taken to the 4x equals 27 is 3 to the 3rd, and that's taken to the e power. So now we multiply those exponents. So now we have 3. Anytime we have a power to an exponent, we multiply the exponent. So we have 8x. And then that 3 to the 3rd will give us 3 to the 3e. Now our bases are equal. So now we can go ahead and set the exponents equal. So we have 8x equals 3e divided by 8. And x is equal to 3e over 8. Logarithmic equation, we can simply set equal a number, so we can simply, anytime we have a logarithm set equal a number, we just put it into exponent form. So we have a base of 81 to the 1/4 power is equal to x squared minus 13. That's 81, the fourth root of 81, which equals 3. And you go, oh, well, shouldn't that be plus or minus? Well, that's the same thing as like square root of 9. Whenever you have an expression like that, we just take what's called the principal square root. So this is a positive 3. And then we have x squared minus 13. Add over the 13, and that gives us 16. Square root, we get x equals plus or minus 4. And now what we want to do is what I like to call eyeball checking, just by looking to see if it would work. In terms of making sure, since the variables in the argument, we have to make sure that this argument is positive. So if I plug in a positive 4, we have a 16 minus 13. That's positive. A negative 4, and for there to be 16 minus 13 as well. So therefore, our solution, both of those make a positive argument, and therefore it's x equals plus or minus 4. Coming down to number 11a, looking at this, I think one of the most common mistakes is probably the natural logging on both sides, kind of like what I did in that first example, the quadratic. It is maybe a little hard to see, but if remember, these are terms, e to the x, just like an x, or just like an a, or just like, you know, a natural long term, I guess. And if we have a term and a term with an e to the x in it, we can factor out that e to the x. Let's see what happens. We factor out an ex. Now we have a 7x minus 14 left inside. And now we see, since it's set equal to 0, which is nice for us, we can set both of these equal to 0 using the zero product property rule. E to the x equals 0, our first one. That's not possible. E to the x has to be greater than 0. And then we have a 7x minus 14, and then we solve for x by adding over 14, divide by 7, and we get x equals 2. Moving on to b. We have two logarithms being subtracted, set equal to 0, so we can condense those two. They both have the same base, so we condense it down to log base 4, and x squared minus 15 is part of the positive logarithm, and log base 4 of 2x is the negative logarithm, so that one goes in the numerator, or the x squared minus 15 goes in the numerator, the 2x goes in the denominator. Set that equal to 0, and now we go ahead and put into exponent form. That'd be 4 to the 0. 4 to the 0, I'm not going to write it, but we know 4 to the 0 equals 1, so I'm just going to write the 1 in the interest of time. And then we set that equal to argument, which is x squared minus 15 over 2x. And we look at that, we need to get x by itself. So nothing what we can do other than multiplying by this top are both sides. So we do that. These cancel, and now we have x squared. I'm just going to move this x squared minus 15 to the left-hand side equals 2x, and we have a quadratic, so we're going to move over the 2x. So we subtract over the 2x minus 15 equals 0. And now we factor that. That will be x minus 5, x plus 3. Sorry if there's some background noise. And now we have x equals 5 and negative 3, and this is something we need to eyeball check and make sure it doesn't make either of the arguments negative, because it makes either of the arguments negative, then it's not a solution. So if we plug 5, I'm looking at 5 first, I plug 5 into there, that would be positive. 5 into there, that would also be positive. If I plug a negative 3 in for there, it would be 9 minus 15, which would make that negative, and it would also make this net one negative, but just the fact that it made one of them negative is enough to cancel it out, so our only solution is x equals 5. Moving on to c, we have log x minus 6, log 2x plus 1. Both those bases are equal, and therefore we can think of it as quote-unquote canceling out the bases, or just simply setting the arguments equal, and then we go ahead and solve by subtracting the x over and then subtracting the 1 over, and we get x equals negative 7. Now we need to look at that. I did box it in, but we do need to, again, eyeball check, and we see if we plug in negative 7 to both of those, it would make both of those negative arguments, so therefore we have no solution. Alright, on the last page now we're doing calculations in terms of our compound interest formulas. Remember, we have our 2, the p 1 plus r over n to the nt. That's when we have some sort of compound interest happening per unit of time, either once in the unit of time, like years is happening once a year, or twice a year, three times a year, and so on. And then our other model is continuous exponential growth, PE to the RT, and we use that whenever we have continuous growth, and that's dependent upon how the question is asked or what situation you're in. Okay, so let's look at A. Bank pays a nominal rate of 6.75, and the compound, it is interest is compounded monthly. Therefore, if it's compounded monthly, we're using our A equals P plus 1 over R, P plus 1 plus R, P times, 1 plus R to the R over N to the NT. Let's see, within these problems, they're always going to give you pretty much every information except for one of the variables. Not always. We'll look at cases where it's not. Those are two-step problems. But we have R, we have N is monthly, the M is monthly. How much needs to be deposited? So that gives away right there how much needs to be positive. We don't have P. So A is $100,000. So I'm going to plug it into the 100,000. I have P, and I have 1 plus a rate of 6.75, so it'd be 0.0675, divide by its compounded monthly, so that would be 12, and then our N again is 12, multiplied by the time. The time is 10 years, so I have a 10 in the in the exponent for the T. So the basic way of solving this, if you look, we have a P with all of that jazz is just a number, so it's P times that, so we want to divide by that. I'm not going to write it out, but imagine all of this is underneath the 10,000, 100,000, and it looks like I forgot one of the zeros. So if I do 100,000 divided by that, all of this goes underneath here. That's what you plug in your calculator. Just make sure you have parentheses correctly. You get P equal to $5,101.20. What is the effective rate? Round to the 100th place. So that's taking the 1 plus 0.0675 over 12 to the 12th to see what this new base would be. And if you do that calculation, you end up getting 1.06963. Subtract off the 1 to get just the rate, which is 0.06963. And we want to round it to the nearest 100,000th, which would be the third number. So we just drop the 3, since that would round down. 6.96% would be your effective rate. Coming to 13, Monday, there were 7,000 bacteria in a pond. In 1 week, the population will double. So in this one, it doesn't tell us continuously, but we can assume, since we're talking about natural exponential growth, that we are going to use natural or continuous growth, the PE to the RT. In this case, RR, they want to use K. So it's saying that it takes how many days? It has 1 week, so I'm going to put that in units of days. So I'm going to go 2 is our A over P. The ending amount is double that of the initial, and it doesn't really matter if there was 7,000 originally, because the ending amount would be 14,000, and solving for T, which we don't have, we'd be dividing by that 7,000, so we simply can write 2 to the E K, and then we're going to put in the year, or the days, which is 7. I'm just going to make it nice and neat and put it in front of it. Natural log both sides to pull the exponent down in front. That gives us 7K. And note, I will write it and instruct on it here, which I'm sure all of you are aware of and understand, but nonetheless I wanted to make sure I cover it. When you pull that 7K down in front, you now have that natural log E, and natural log E equals 1, because E to the first power equals E, so that goes away. Now we divide by 7, and now we have natural log 2 over 7, and that gives you approximately a K value, which is your rate of 0.099. Now, since this is doubling, that means it's exponential growth. Your K, or in this case K or R, depending on what variable they want to use for that rate, if it's doubling, that K value should be positive, which it is. If it's exponential decay, then that K value should be negative. So that's just kind of like a general check to see if you did your math right on that. And then it says find the population after 15 days. So find the population, that's our ending amount. A equals P, which was 7,000 originally, times E to the 0.06963
0.099, 15 days. I picked the right units. If you picked a week, then you would just have to do 15 over 7 to make sure you have your 15 days in units of weeks, and then make sure you answer the question accordingly in terms of I'm sorry, that wouldn't actually matter because you're asking for a population. So if we do that calculation and we end up getting 30,915 would be the population after 15 days. How long will it take the population to reach 100,000? So we have 100,000 as our ending amount. Our original amount was 7,000. Again, we have our rate of 0.099 as we're just making the assumption that that rate of growth is constant. And, oops, I forgot the e in there, sorry. So 7,000 e to the 0.099 t. And then we just got to solve for t, so we're going to divide by 7,000. So now that cancels out. So now we have, 100 over 7 if we just reduce that. And we have an e.099t. We're going to natural log both sides. And then you have natural log 100 over 7 equals 0.099t. You had that natural log there. I'm just going to clean that up there. There's a t. You have that natural log of e next to it, but that has canceled out. And now we divide by 0.009. Those cancel. And then this right here, make sure you just put parentheses around that after the 7. So you have natural log of 100 over 7, and parentheses, and then divide by 0.009. And if you do that in the calculator, you'll get a t, or time, of approximately 26.8 days in order for it to get to 100,000. Find each amount to the nearest cent if $700 or $7,500 invested 5% for 30 years, compounded yearly. So yearly, we know we're going to use our 1 plus r over n to the nt. We're starting out with 7,500. We have 1 plus the rate, which is 5%, so it's 0.05, and that's to the 30th power. Plug that into your calculator, and you get 32,414.57 cents. If it is compounded quarterly, all the same, except we now have 1 plus 0.05, and since it's compounded quarterly, we do the 4, and then we have 4 times 30. Plug that into your calculator, and you get 33,301.60. And then lastly, continuously, we are going to use PERT here, or PE to the RT, or PE to the KT. 7,500 E to the 0.05 30 times 30, excuse me, and that will end up giving you A equals 33,612.67 cents. Now, just a quick thing, if you note on all of those, you notice there's really not much difference. If you're investing $7,500 over 30 years, the difference is a matter of, a few $100-ish on all of those. What you see is the way that it's compounded is really not what's going to make a significant difference. What's going to make the biggest difference, long story short, is the rate. So the higher the rate, the better the return.